And by the way, we have food, well, rather granola snacks and drinks, but you can only take them at the end of the seminar and not in this room. Nobody is allowed to eat in this room. Unfortunately, we have to do.
Okay, hi everybody, I'm Alex. It's really good to be back in person in a seminar with anybody. This is one of the first ones I've been back to in person, so it's really good to see everybody. The title of the talk today is Model-Based Robust Deep Learning. It's going to encompass kind of a bunch of work I've done over the last few years, trying to make different kind of deep learning algorithms and models more robust. So to start off, I'll say a couple of things about the successes of deep learning in the last few years. And at least give a partial answer to why are we using deep learning so much. So on the left here, I'm showing kind of the recent progress on the well-known ImageNet benchmark. So this is kind of one of the canonical benchmarks that people use in image classification. And as you can see, as we progress from 2012 onward, we've actually approached and surpassed the human level performance. So here, this red dashed line here is showing kind of how well a human does it recognizes the images in this data set. And as of about 2017, kind of deep learning algorithms and architectures surpassed this human level performance. So this is to say that at this point in time, on certain tasks, deep learning does significantly better than humans can do. And on the right, I'm showing kind of a more real world example of a perception system that's mounted on a self-driving car. And so the job of this perception system is to kind of recognize different objects on the road and try to recognize pedestrians as well to allow the car to successfully navigate in this kind of dynamic environment. So this is all to say that over the last few years, we've seen kind of a lot of successes in a wide variety of applications for different deep learning based methods. And as this kind of progress has manifested itself, what we've seen is also deep learning being adopted in what I would call safety critical applications. So at a high level, what I mean by safety critical applications are kind of applications or domains where the decisions or recommendations of a deep learning system might impact the well-being or safety of nearby humans. So some good examples of safety critical applications are your autonomous vehicles. So you might consider that if this self-driving car system was trying to identify people in this crosswalk, it's very important that it robustly identifies these people, because if it misidentifies someone, it might speed up and endanger the well-being of these people. Another good example is robotics, perhaps closer to what some folks here are working on in GRASP, where especially when we have robots working alongside humans, it's really important that the decisions made by deep learning systems deployed, say in robotics, don't kind of negatively impact the safety of the nearby humans. And a final example here is medical imaging. This is something I'll talk about quite a lot in this talk. So in this setting, it might be the case that the detections or recommendations of a medical imaging system might impact the downstream care that a person receives. So it's really important that these kind of decisions are quite robust. And the thing I want to highlight amongst all three of these applications is that when we deploy deep learning methods in these sorts of safety critical applications, where our decisions are really going to affect how safe people are, it's quite important that the systems that we deploy are in some sense robust or trustworthy so that we know they're not going to make a mistake. And at a high level, that's kind of the motivation for everything I'm going to say today, that deep learning methods need to be made robust to kind of common changes that you might see in these sorts of safety critical environments. And so with that motivation in mind, I want to highlight three key takeaways that I hope everyone gets from this talk today. So these three takeaways are the following. So first, I'm going to just empirically demonstrate, hopefully, across a wide variety of different kind of application domains, that deep learning lacks robustness to what we might call common shifts in data. So in other words, in a lot of applications, data can vary in all sorts of ways. And while we might have some data to train our deep learning model on, it might be the case that at test time, you might see kind of a different distribution of data. And as it turns out, throughout many different applications, which we're going to see in a few slides, the performance of these deep learning systems degrades fairly significantly when the distribution of the data seen at inference time changes. The second message is that, well, not really a message, but more just a statement that in this talk, I'm going to propose a unified paradigm for thinking about robust learning in the context of deep learning. So we're going to use these examples that we started with to kind of motivate this need for an overarching paradigm of how we can think about training robust models. And the key idea here is that we're going to try to leverage the data that we have available to us to tell us something about the distribution shifts that we might see. And then finally, the thing I'm going to leave you with at the end of the talk is that if we use this paradigm smartly, and if we kind of figure out how to learn distribution shifts directly from data, then this can be used directly to significantly improve robustness across a variety of domains, including tasks like domain generalization, transfer learning, robust certification, and all sorts of things. And at the very end, I'm going to try and leave with just some directions for future work in all sorts of different directions that I hope will be kind of, useful for folks that are thinking about things in this area. And so to start, I'm going to start this talk with this kind of first point up here, talking about the extent to which deep learning is vulnerable to kind of common shifts in data. Does this kind of framework make sense? Any questions so far? Okay, so let's start off when talking about kind of the fragility of deep learning with kind of the canonical example that's been studied over the last few years. And that's the setting of adversarial robustness or adversarial examples. So I know many people might be already familiar with this setting, but for those that aren't, let me just recap kind of what happens in this application. So we think about our data as living in some Euclidean space RD, where if we're doing image classification, D might be something like the number of pixels. And each, say, image in our data set is just a point in this Euclidean space. So something like this. Now, when we go to train a deep learning system on kind of our nominal data points like this, we can achieve classifiers, or we can train classifiers that do very well. So in other words, I could have a classifier that is able to correctly identify the contents of this image if this was a classification task. And as we'll see in a few slides, we can achieve 98, 99% classification accuracy when we're just given some data and asked to classify it. But then the question becomes, well, what if I didn't want to classify exactly my image? What if I allowed an adversary to perturb this data by small amounts of noise? So what I mean by that is, say I took this data point, I drew a Euclidean ball around this data with some radius epsilon, and I allowed an adversary to perturb this data by some perturbation delta, where the only constraint that I put on delta is that it's bounded in norm by this number epsilon. So it turns out that if I then pass this adversarially perturbed data to this state-of-the-art classifier that I've previously trained, it quite often tends to misclassify this as something else. So in this case, a given. This is kind of the canonical example when we think about kind of adversarial perturbations. And this is kind of a big problem because what you'll notice here is that the original image X and the perturbed image look exactly the same. Like I can't tell the difference between the two. But for some reason, the deep learning system is not able to understand that these are the same thing and makes a misclassification. So to share some numbers with you here, the performance of just plain empirical risk minimization on this data set is around 94%. So we can do quite well when we're just asked to classify our nominal data. But when I allow an adversary to perturb this data in the way that I had in the previous slide, I can reduce the performance of this classifier to less than 1%. So this means that my classifier is now doing worse than random on data that looks exactly like the data that I started with. And this is a big problem, right? This is a very clear demonstration of the lack of robustness of deep learning. Now, eventually, what I'm going to show in this talk is that there's been kind of a lot of research that's been done in this direction toward improving the so-called adversarial robustness of deep learning. And in fact, the methods that have been kind of proposed can significantly move this number back up. And just to preview what's coming later in the talk, toward the end, I'll talk about an algorithm that we proposed that just was accepted at NERBS this year that kind of advanced the state of the art very slightly in this field. But of course, this is something of a synthetic example, right? I'm like allowing an adversary to artificially just add noise to my data. So you might ask, well, is there kind of a more realistic example where deep learning is fragile to distribution shifts? And the first kind of real world example I want to give you is that of spatial transformations. So by spatial transformations, I mean anything where I'm kind of rotating or scaling my data according to some geometric shift. So on the top, I'm kind of rotating my data, and here I'm kind of scaling my data so it becomes larger or smaller. So it turns out that, like the case of adversarial examples, this can also really hurt my test time performance. So in particular, if I were to take kind of an image like this, and I were to allow an adversary to kind of arbitrarily perturb it according to one of these spatial transformations, so maybe I rotate it a bit, I scale it, and I rotate it back, then I can really degrade the performance of deep learning systems. Now, to illustrate, here's kind of a plot similar to the adversarial examples case, where in the blue, I'm showing just the clean performance of classifying these MNIST digits. And now I'm showing the performance when I allow an adversary to arbitrarily kind of rotate or scale my data. So notice that I can, again, reduce my performance to essentially nothing just by choosing a really bad spatial transformation. So this is kind of clearly, yes, Thomas.
Do you limit like the degree at which, for example, rotate?
Yeah, that's a good question. So in this case, the answer is yes. So this example, this actually was the extent to which you rotate it, so that -20 to 20, because if you were to rotate a 6 upside down, it would kind of result in a 9, and then that would actually be a different image. But yeah, we're assuming here that the transformation is kind of keeping the label invariant. It's a great question. But here again, we're seeing like a really kind of stark illustration of the lack of robustness of kind of deep learning methods. The difference here between the case of adversarial examples, of course, is that now the distribution shift that we're dealing with is kind of semantic, or it's we can actually see the difference. It's perceptible. Whereas in the case of adversarial examples, we couldn't actually tell the difference between the perturbed image and the original image. And so moving beyond kind of this MNIST example, let me share with you kind of a real world example where these distribution shifts manifest themselves. So let's consider a medical imaging example where my job is to do cancer prediction. So it's a binary classification task. I'm going to get a picture of a group of cells. My job is to identify whether there's a tumor or not a tumor in this group of cells. I'm going to assume that my data is split into kind of 2 groups. I have a group of data from some set of training domains. So this might be some hospitals where I have kind of data. And then I'm going to have another set of data that's from a set of test domains from completely different hospitals that my training data is from. So let me illustrate that a little bit. So abstractly, there's some space of all hospitals. Each point in this space corresponds to a hospital from which I can sample data. So here's the first hospital. I get access to some data from this hospital, another, and another. So these hospitals might constitute my training data. So I can maybe collect some samples from each of these hospitals. And then at test time, I'm going to get data from a completely different hospital. And my job is to use the training data from these green hospitals so that I can classify well without access to any data from the hospital that I see at test time, which is this blue hospital. So here the story is similar to what we've already been seeing. So I can take my training data. I can train a classifier that performs very well, say 98%. And then at inference time, when I get data from this new test hospital, my performance again drops significantly. And here's the numerical kind of example here. So this is from this actual data set, this hospital data set. And I'm showing kind of the algorithms I'm showing are both ERM, which is kind of vanilla training, and also some algorithms that are actually designed to do out of distribution generalization. And notice that, so the blue bars are showing kind of the performance on these test hospitals or these training hospitals. And these kind of gold bars are showing what happens when I evaluate the performance of this classifier on this unseen test hospital. So notice again that the performance has dropped pretty significantly. So the goal of this talk is really going to be that given this observation that performance can drop significantly when the distribution of data differs between training and test time, I want to design methods that can kind of overcome this distribution shift. And ultimately, what we're going to see in this setting of medical imaging is that we can design algorithms shown on the very far side there on the right that can really overcome this distribution shift by learning directly from data. Just to highlight kind of the breadth of this kind of mindset of thinking about distribution shifts, there's just 2 more examples that I want to share very quickly. So one is kind of, and these are both motivated by the initial slide. So another kind of distribution shift that you might see is kind of one in autonomous vehicles where the weather conditions may be changing. So you might have some nominal data point, say this image of the sign in sunny weather, and nature can arbitrarily perturb this data and produce kind of all sorts of different weather conditions. This also kind of fits in this framework of distribution shifts that we're thinking about. Another example that I wanted to share is that of robotics, since kind of we're all in the GRASP lab. This is from a recent paper at L4DC. The idea was to train a grasping robot on some nominal grasping task, showed kind of on the left here. And the idea is that it wants to pick up things in the basin. And when there's no shift present in the data, it achieves kind of relatively good performance, 86%. But when I slightly change the conditions here, so for example, when I change the lighting conditions or I change the background in this basin, the performance drops quite a lot. So this is to say that these kinds of distributional shifts really manifest themselves in all sorts of the applications that we care about. Okay, so that was the first part of the talk. We went through a bunch of examples of how distribution shifts might manifest themselves in different applications, starting from like the synthetic adversarial examples, moving on to more general distribution shifts. So given that, let's move on to the second part, where I want to ask the question, can we design a paradigm that allows us to think about all these sorts of distribution shifts under one umbrella? Okay, so I'm going to add a little bit of notation to this problem that we've been sort of developing with respect to distribution shifts in data. And on the left, or on the, I guess, your right-hand side, I'm going to have a running example that kind of illustrates the quantities that are involved here. So to start, let's let X and Y denote some random variable pair. For simplicity, I'm going to talk about classification tasks today, but this could also be kind of extended to other kinds of tasks. So here, X is something like my image in a data set, and Y is something like the label. So in our medical imaging example, X might be the distribution of images, and the label might be the distribution over, like, do I observe cancerous cells or non-cancerous cells? Now, I'm not going to get to directly observe this random variable pair X and Y. I'm going to assume that I get to observe this kind of random variable pair in different domains or environments, where the domain is indexed in some set EAll. So EAll, think of it as kind of the set of all environments. And what I mean here is that if we again consider this medical imaging example, the set of all domains in which I might observe my data might be like the set of all hospitals, like we had on the previous slide. So each of these domains is going to induce a different distribution on my data. And I'm going to call each of these distributions XE and YE. So concretely, XE, YE is the observation of X and Y in a particular domain E. So for example, XE, YE might be the observation of data at a particular hospital. And as we move from domain to domain, we're going to see different realizations of our data. So the key point here is that this number, or this variable E, is describing some sort of underlying process that's varying our data. In this case, the data is varying from hospital to hospital with kind of the stain pattern that's being observed or the quality or resolution of the imaging equipment that's being used. And ultimately, given data from some subset of these domains indexed by E, our goal is going to be to learn a classifier F that allows us to classify, well, no matter what domain we're in. So in other words, I want F of XE to be approximately equal to YE for any domain that I might choose. This would be the idea of robustness that I want to enforce. Okay. Now to develop this a little bit further, let's place some natural assumptions on this kind of problem setting that I had on the previous slide. In particular, I'm going to have two assumptions. The first is that there's some underlying, what I'm going to call domain transformation model G, that parameterizes this map from the underlying random variable X to this random variable XE in an environment E. So think of G as a function that just takes this random variable. Say X here is just over the real world, like physical manifestation of our cells, and allows us to observe it in different environments. So when I push X through this function G for different values of E, I'll get three different realizations of my data. So really this G is just parameterizing the distribution shift that I'm seeing. Now the caveat here is that we might not necessarily know G a priori. For example, in this medical imaging example, I don't know a priori, I can't write down a mathematical expression for how I map my data to different domains. And again, I'm going to get back to this point later, but for now, just assume that this function G exists, and we'll talk kind of later about how it might be obtained from data if you don't already know it. And kind of the concomitant assumption here is that this function G that I'm assuming I have does not change the label of the data Y. So in other words, no matter how I pass my data through G, the label of each of these data points is going to be the same. So it's not that unreasonable to assume that for each of these cells, since they look quite similar, that this isn't going to change the fact that these cells have cancer or don't have cancer in them. So again, this second assumption is just that G is not changing the label. Okay. So this is that was like a kind of a 2-slide overview of the notation of this problem setting. And now that we have this kind of notation in mind of this function G in this set of all environments, let's return to those examples that we had earlier in the presentation, and let's think about kind of what they all had in common. And in particular, what they all had in common was a perturbation model G, or a domain transformation model, as I called it on the previous slide, and some set EAL of environments. So in the first case of adversarial examples, the perturbation function, so the mechanism by which I perturb my data, was a very simple one. Does anyone want to guess what it is here? Thomas? Yeah, exactly. It's just, so the mechanism by which I'm varying my data is just an additive function. So I'm just adding something to my data. So I'm moving from X to X plus E here. And I'm looking over this kind of, as Thomas said, this Euclidean ball. So just some set of bounded perturbations. In the case of spatial transformations, I have a somewhat similarly simple example in that the way by which I can perturb my data is just some rotation matrix, say, or just some scaling function. And for the example of rotations, when I set EAL, so the set of all possible environments, it's just kind of the minimum or the maximum angle that I can look at. So this is just how much I'm allowed to rotate my angle. So this is back to Thomas's earlier point of I can't arbitrarily rotate my data. Now, when it gets challenging is in these kind of more general distribution shifts, where, as I said earlier, I don't actually know what this function G is or what this set of all hospitals EAL is. And when this happens, you know, a lot of the work that's been done on this subject kind of stops. So people in general haven't been thinking quite a lot about how I deal with general distribution shifts that I can't write down using an analytic formula. And so what I want to address, at least partially in this talk, is, well, if I don't know the distribution shift a priori, can I use data to learn it? And the answer, at least in short, is in some cases, you definitely can use data to learn the distribution shifts that you'll see. And the main tool that I'm going to use to learn these distribution shifts are what are called multimodal unsupervised image-to-image translation networks, which just does a fancy word for GANs, basically. So we're going to use data and GANs to try and learn this distribution shift that we're going to see. And the idea is the following. So given an input X, I'm going to encode X using some neural network to a 2-level semantic representation or two-level latent representation. This first part of the latent space is what I'm going to call the semantic representation. So this is, at a high level, everything that's needed to completely reconstruct the main contents of this image. So this is something like, if the distribution shift is just in the color of this image, then the semantic representation is something like just the grouping of the cells, something that would be needed to reconstruct the label. And the second part is what I call the nuisance representation. So this representation is meant to capture any sort of nuisances in the data, any sort of distribution shift. So in this case, this would capture anything particular to the hospital at which we observe this data. And the idea is that I'm going to first encode this input, and then I'm going to decode it and reproduce my input. But the special thing about these kinds of networks is that if I were to, instead of directly encoding and then decoding this image, I could replace this nuisance content that's particular to the hospital that I observed it at with some randomly sampled nuisance vector. And then I could decode the resulting latent representation. And what we can do just simply using data is leverage this kind of framework to learn distribution shifts directly from the data. So there are subtleties here in how you train the GANs and how this architecture works. This is kind of a simplified version of what's going on here. But I hope this gives you an idea of sort of how we can think about like parameterizing a distribution shift with a deep generative architecture. And so high level here is that by varying this nuisance representation, we can get some sense of varying the environment of a given data point. And this is kind of the main tool that I'm going to be using toward capturing real world distribution shifts in data. Just to share with you some samples from different data sets that we've worked on. So this left-hand side column here are kind of data points from 3 different data sets. And on the right, I'm showing samples from these GANs that we were training to capture distribution shifts. So the top one, you can see that in this case of medical imaging, I can take an image and I can like pretty successfully mimic the conditions that I showed earlier at different hospitals. In the second data set, you'll notice that I can really get a hold on kind of the terrain of these kind of aerial images and so on. So this is just to say that this is a really good tool for capturing distribution shifts. Okay, so at a high level, what we just talked about was a paradigm for robust learning, right? We talked about how to think about distribution shifts using kind of a statistical language. And we also discussed a tool where I could learn distribution shifts directly from data if I didn't know it already. And so these are kind of the key ingredients for robust learning in deep learning problems. And so kind of in the last final part of this talk, I'm going to show how this paradigm can be used to significantly improve robustness on a number of different benchmarks. So I'm going to consider problems from a few different fields, but the unifying idea is going to be that in general, I'm not going to know the distribution shift, so I'm going to try and learn it from data, and then exploit different statistical and optimization techniques to improve my performance across all of these domains. Okay, so the first work that I want to talk about involves the setting of domain generalization. So if you're not familiar with this setting, let me just recap it very quickly. So the question we're trying to answer is, can we generalize to data from domains that are not seen during training? So this is kind of similar to this hospital kind of application, where I get some training domains at training time, and then I need to perform well in a completely unseen test domain. So a little bit more concretely, I'm going to get access to kind of 3 subsets: e-train, e-validation, and e-test. My job is to train using the data from the training domains, to tune my hyperparameters using data from this unseen validation domain, and then to evaluate the performance of my classifier on this completely unseen test domain. And as I said earlier, our approach here is that as we don't know this distribution shift, we're going to learn G using data drawn from the training domains, and then we're going to use that G to improve robust performance on this unseen test domain. So let me talk a little bit about how we did that. So the big idea in domain generalization is to try and do well even on the worst case. So this is the idea of having a classifier that does well in any domain. Now, the way to write this down in terms of an optimization problem is the following. So I'm going to write down a min-max optimization problem. The inner max is over the set of all environments, and the outer min is over some space of classifiers. So let me break this down just a little bit. So let's start off by thinking about this inner problem. So again, this inner problem is a maximization over the set of environments. And I essentially want to find the worst case environment. So the environment that maximizes my risk over the data distribution. So here, L is just some loss function that tells me how well I'm doing at classifying X's from Y's. And notice here, F is taking some data point G of X comma E. So F is being perturbed according to the distribution shift that we have on hand. And again, idea here is that if we have access to the set E all, and each environment E is a point on this kind of abstract space or manifold of all hospitals, I want to look over all possible realizations of E and find the one that makes my classifier do the worst. So in other words, I want to search over this space, E all. Notice how the realization of my data is changing. And I want to find the environment that causes me to do worst. So that when we move to this outer problem here, we're finding a classifier that will do well even on the worst case domain. So I might take this worst case data point, I'll train a neural network there, and ideally I will do well even in the worst case. So in any worst case realization of my distribution shift. Now, the insight in this paper is that under the assumptions that we made on the particular form of distribution shift, in particular the assumption that the labels remain invariant to G, we can rewrite that min-max problem as a constrained optimization problem, where now the objective is something like empirical risk minimization, and the constraint is just saying that F should not change its prediction when data is varied by this function G. So this is kind of an empirical risk minimization problem with some invariance-based constraint. So this is completely equivalent to the min-max problem I had in the previous slide, under the assumptions that we've already made in the unified problem setting. So of course, solving this problem is still challenging in the context of deep learning. It's quite hard to enforce hard constraints on neural networks. So what we do is we formulate the empirical dual problem here. And I'm not going to go into the details of kind of how this works, but the main tool here is duality. And we're going to use kind of some primal dual style algorithms to solve this empirical dual problem, where now G is our learned function, so our learned distribution shift that we learned using GANs. And we'll see what happens. So before presenting some experiments, let me just give some context to these experiments. So this quote comes from a recent, very large scale empirical study of domain generalization problems. It says, when equipped with modern architectures and data augmentation techniques, ERM achieves state-of-the-art performance in domain generalization. So in other words, despite the fact that dozens and dozens of algorithms have been proposed for this setting, ERM, or just plain vanilla training over the set of training domains, is the best thing that you can possibly do empirically. And so, the fundamental question arises, well, is it actually possible to outperform a well-tuned ERM in the setting of domain generalization? This paper essentially argued that it may not even be possible. So given that kind of motivation, let me share some results. So we took some of these standard benchmarks that people care about in domain generalization. We learned the distribution shift, and we were able to, just by learning this distribution shift directly from data, significantly improve performance out of distribution. So on this colored MNIST benchmark, which kind of has spurious correlations between the digit and the color, we got a 30% improvement using this primal dual scheme. And on this medical imaging data set that I've been showing you throughout this presentation, we got something like a 20% improvement over ERM. So this is all to say that ERM is not the fundamental limit of domain generalization when you think about learning your distribution shift directly from data. Okay, let me move on to, yeah, Thomas.
So what you showed mentioned ERM with data augmentation. So if you would put, let's say, if you generated augment your data with, let's say, your GAN, what would happen? That's
a great question. So we did this experiment in the paper. It improves the performance of on out of distribution well beyond what ERM can do, but it doesn't perform as well as the primal dual that we proposed. So there's kind of a family of algorithms that you can think about with respect to this when you learn your distribution shift. I mean, you can add regularizers, you can do data augmentation, you can do primal dual, and it turns out that they all work. It just happens to be the case that when you really want to enforce this hard invariance constraint, that the primal dual thing is the tool that you want to use. But yeah, that's a great question.
So,
yeah.
So how much time it takes to do the primal dual?
Good. So it adds a very small amount of computation time. So the thing about the dual problem is it's a linear problem. So the update doesn't involve taking gradients. You can just update based on the constraint violation. So really you just need to do a few multiplies and additions extra per iteration. So it doesn't, effectively it doesn't add any runtime just because of the high cost of computing the gradient, which all of the algorithms do. Okay. A closely related experiment is one of kind of outer distribution robustness. So the question here, similar to the last paper, was can we use data from one data set to improve outer distribution generalization on a different data set? So the setting would be something like I have street signs from one country, and I learn a model of my distribution set, say from daytime to nighttime. So say I learn some G that parameterizes this shift. And then I'm given a completely new data set. So this data set Different from the previous couple of slides on domain generalization, this data set may have completely different labels, may have kind of nothing to do with the previous data set. But it turns out that I can still use my generative model to parameterize the same transformation. So in this particular case, this data set of street signs is the kind of German street sign data set. And it's like kind of a very long tail distribution. And I'm using a data set of street signs that were collected in the US. So these are completely different street signs. The labels are not the same at all. But the fact of the matter is, when I learn my distribution shift, it's often the case that I can reuse this model on a completely new data set, which is quite useful. See what I got here? Right, because it allows us to solve kind of a closely related optimization problem to the previous one. So whereas in domain generalization, we consider kind of this worst case realization of a domain, maybe even a slightly harder problem is to consider kind of a worst case realization of a particular data point, which is what I'm doing here. So the difference here is now I move the max inside, and I want to think about learning a predictor that's invariant or robust to a worst case perturbation of each data point rather than of the expectation itself. And so the way we think about this in the street sign setting is if we think about this inner problem, this inner maximization, we're given a particular data point, X, and we want to find the environment E that causes the classifier to do the very worst that it could possibly do. So what that looks like is we're given this kind of nominal data point here, and I can search over the space EL to try and find the number or the index variable E that causes my classifier to have very high loss. And in this particular setting of the street sign classification, we showed that when you learn this generative model on this completely different data set, and you solve this optimization using just standard kind of adversarial training ideas, that you can, again, significantly improve the performance despite having access to no more data on the data set that you want to classify on than any of the baselines do. So this is kind of a question of transfer learning. This is a question of outer distribution robustness. But the key point here is that even if you don't have any data that corresponds to your distribution shift in the domain that you want to classify well in, if you have a model from previous kind of distribution shift, you can reuse it again and again, which has kind of also very nice properties in terms of the computational cost of learning these distribution shifts. Okay. Next example is related to previous ones, but it's solving kind of a different problem. But it's still in the same family of trying to deal with distribution shifts, except for rather than asking how well can I train a classifier to perform on an unseen test domain, here the question is, can we certify the robustness of a classifier to some distribution shift? So in other words, can I hand you a certificate that if you see a particular distribution shift, then the predictions made by your classifier, your predictor will not change. So this is a slightly different problem. So again, it's nice here to think about the motivating example of kind of spatial transformations. So this problem would be trying to address how much can I rotate my data such that whatever my classifier outputs does not change. So such that this thing is still classified as a 9. And the ideal picture is something like this here. So on this bottom axis here, I'll measure something like the severity of the distribution shift. So for example, this far left might be no distribution shift at all. So say a 0-degree rotation. And as I move across here, this would correspond to larger and larger rotations. And what I show for each of these different distribution shifts is something like a histogram over each image in the data set, where I'm showing the maximum severity that that particular piece of data can take before the classification flips. So this histogram is kind of showing, kind of just in one graph, the amount of robustness that I can certify on a particular data set. Now, let me tell you a little bit about how we went about solving this problem of trying to certify the performance of classifiers against kind of these real world distribution shifts. And it's basically a 2-step procedure. So as we've done before, the first step is, of course, to learn a generative model that captures kind of the distribution shift that we're going to see. So that might be something like this, where my generative model captures maybe something like the weather conditions in images, or maybe something like the spatial transformations that I have on the previous slide. And it produces kind of, this generative model ideally should produce kind of some range of distribution shifts. So what I'm showing here is just a gridding of the latent space here of this generative model. So this is this nuisance space that I discussed earlier. And what you'll notice here is that as I walk across this gridding in the latent space, I'm kind of getting this different severity of distribution shift. So the top row here, I have this input image. And as I walk along the latent space of this generative model, the kind of size or scale or brightness of these images is changing. And it gives us some notions of distances and distribution shifts, right? So I can kind of equate or I can compare the distance in the latent space to kind of the severity of the distribution shifts that I'm seeing. And so given such a generative model, I can use this kind of latent space interpretation of how severe my distribution shift is to certify robustness of classifiers to perturbations in this latent space. So in other words, I can look over all the sorts of images that can be generated in my latent space of my generative model. And I can provide kind of those kinds of histograms that I had in the previous slide, or I can find counterexamples of minimally perturbed images that will cause my classification to change. So here on the top row, I'm showing images from the original data set. And for each of these shifts, I'm showing some sort of distributional shift, which is as small as possible such that it flips the classification. Okay. Another related problem is that of long-tailed robustness. This is a paper that actually was just submitted last night. And the idea here, similar to the previous ones, is we have some classification task. And we want to assess the extent to which neural networks are invariant to distribution shifts. But rather than training neural networks or certifying their robustness, we want to measure invariance here. So in the setting of long-tailed classification, generally you have a data set with very many classes. Some of the classes, what we might call the head classes, have a lot of data. So that would be these classes here. And most of the classes have very few data points. So something like this. So this kind of green region here is the data, or the classes for which I have a lot of data. And for the majority of classes, I have very little data. And so in this setting, the question naturally arises, well, what are the invariance properties of a classifier trained on this distribution? I mean, somewhat intuitively, you might expect that when I apply transformations to data or to classes that I've seen a lot of data for, then the classifier should be quite invariant to these transformations because I've already seen a lot of examples from these classes. Whereas if I were to see a class for which I've seen almost no data for, you might expect that if I were to apply some sort of distribution shift, then I wouldn't be invariant at all to this sort of thing because I haven't seen any examples from this class. And so really the idea in this paper is just to assess the extent to which this is true using kind of learned distribution shifts. So again, the main idea here to kind of measure the extent to which deep learning kind of models are invariant or non-invariant in kind of the long-tailed setting is to train the sort of generative model that captures distribution shifts on the so-called head classes, so the classes for which I have a lot of data, and then to use G to form data augmentation on the tail classes. This will give me some idea of how invariant my classifier is to the sorts of transformations that I can capture with G. And so just to show you a few examples of the distribution shifts we considered. So the top row is showing kind of the distribution shift of dilation on a class that's taken from kind of one of these head classes, so a class for which we had a lot of data. And then the second row is showing kind of a data point from the tail class, so a class for which we had very little data. And notice here that this generative model that we learned, despite the fact that it's not really seeing any data from these small tail classes, it's still able to effectively transfer this distribution shift to classes that it did not see at training time. And so the result of this is the following. So we were able to kind of make these plots that show kind of how invariant these long-tail distributions are. So on the x-axis, we're showing the class size, and on the y, we're showing some measure of invariance, where kind of a lower number means that it's more invariant. So you can see that for classes for which we have a lot of data, which are further to the right, we're kind of much more invariant to these sorts of distribution shifts that we can capture. But as we get kind of fewer and fewer classes, the invariance kind of goes down quite significantly. But what we found is that when you do data augmentation with these kind of learned distribution shifts, where you transfer the invariances from the head class to the tail class, which is this green line here, you can kind of improve this invariance. So kind of the conclusion of this is twofold. One, that these kind of long tail distribution shifts are quite vulnerable to these sorts of non-invariant properties. So invariances that I learned in the head classes won't necessarily be transferred to the tail classes. And also that we can improve this by doing just data augmentation with a learned distribution shift. Okay, and then to wrap up this talk, I want to return to the setting of adversarial robustness. We've talked a lot today about learning distribution shifts. And of course, this problem of adversarial robustness is not one where you need to learn a distribution shift. But it actually, one of the really interesting things about this problem, at least that I've seen recently, is that it gives really, really nice insights into how we might move forward in terms of dealing with real world distribution shifts. So let me tell you a little bit about why I'm kind of really excited about this problem is giving us some tools to work on kind of the more general problem of distribution shifts. So again, we've already kind of considered this problem. The main question is, can we improve the extent to which we can defend against these sort of adversarially chosen perturbations? So we had this kind of example where we're perturbing our data by some imperceptible amounts. If we consider some robust optimization problem where here we're just additively perturbing our data. Now, just to give some context, there's been quite a lot of research on this field in the last few years. So here I'm showing a plot of kind of the cumulative number of papers that have been written on this subject. And notice that we're kind of very quickly approaching 4,000 cumulative papers. And progress has somewhat stagnated in this field. And although it's received quite a lot of interest, you know, it seems as if we're not making real progress on the benchmarks that people seem to care about. Which is all to say that we're kind of in need of some new ideas, I think, in this field, if we're going to kind of go beyond the limits that have been kind of observed in practice so far. And so to address this problem, we thought, well, rather than solving that problem on the previous slide, can we kind of rearrange this problem, or can we rewrite this problem in a more convenient way? And so what we did was we started with this kind of min-max problem. We used just a standard epigraph trick to turn this into a constrained optimization problem. Where here now I have a semi-infinite constraint here where I need this constraint to hold for all x, y, and all environments E. And then the main theorem of this paper showed that actually this constrained problem is equivalent to another problem where instead of having a max inside, now I've moved the max to the outside. So the difference here is that also that whereas this inner max here has kind of this maximization over the set E all, now I have a maximization over lambda in this set P, where P is kind of a set of probability distributions with taking support over this set E all right here. And of course, there are very mild technical conditions that are needed for this theorem to hold, but in practice, these are actually ones that will hold. And the insight that this gives us is that rather than just optimizing over worst case perturbations, we can actually optimize over distributions over perturbations. In other words, if I were to take this new inner or outer maximization problem over this set P, I can look at full distributions over perturbations rather than just trying to find a Dirac distribution at the worst case perturbation. And so this might not seem like a big result at first, but it's really nice because it actually allows us to think about this problem of optimizing over distributions and finding and sampling from a worst case distribution, which is a problem that a lot of people have thought about. So in particular, to go about solving this kind of distributional optimization problem, we're going to use some sort of just Hamiltonian Monte Carlo to try and sample from this optimal distribution. What we found was that just by transforming this min-max problem and by applying this kind of out-of-the-box Langevin Monte Carlo idea, we could both improve the adversarial robustness and the clean performance on CFAR 10 and MNIST and other benchmarks that we tried. So this is exciting from the standpoint of adversarial robustness research because it allowed us to kind of advance things a little bit in terms of what the fundamental limits are in these data sets that people care about. But the thing I think that's really exciting about this result is that it actually applies not only to additive perturbations, but it holds for any sort of distribution shift that you might have. So in other words, we could cross out this kind of adversarial robustness idea. We could think about this more general problem where I've replaced the additive distribution shift with a general distribution shift G. And we can note that it's equivalent to this new min-max problem, for which we have a lot of tools to solve. So what I'm really excited about is kind of using these tools and attacking these kind of new problems for general distribution shifts, because I think this gives us a really nice way forward for kind of future research into kind of dealing with distribution shifts in the context of deep learning. Okay, so that's basically all I had to say today. I just want to recap these 3 takeaways that I had from the talk. So we started off by talking about different examples of how deep learning is vulnerable to different kinds of shifts in data. We proposed a unified problem setting for thinking about robust deep learning in terms of modeling distribution shifts with kind of deep generative networks. And we showed that this paradigm can be used to significantly improve performance on different kinds of challenges like domain adaptation, domain generalization, and adversarial robustness. And so I'll just leave you with a couple of future directions that we have. There's a lot of room here to kind of expand the ideas. So one natural thing is to expand this to kind of ideas in control theory. There's some really nice connections between like biosimulation metrics and these kinds of invariants that we're learning. Also with barrier functions. So it'd be really interesting to see what we can do moving forward by not considering just a static setting of classification, but moving to kind of a more sequential decision-making task. There's also an opportunity to do robust learning on graphs. So you might ask the question, is there a natural idea of distribution shift or generative models for graphs? It turns out that there are, and it's a really exciting kind of interesting problem to think about, not just this image classification setting, but moving to more general data structures. Of course, there are applications to robotics. I think this is a really great example of why we need tools like that allow us to deal with distribution shifts for robotics. Because in sort of safety critical application, performance drops of this magnitude are very likely not acceptable. And the final thing is there's a lot of really nice theoretical directions that this work can go. There's questions of how you do optimization on kind of these manifolds in the latent space. We're looking at kind of different causal inference or statistical interpretations of this work, which is also like a really exciting direction. So that's all I had. I'm happy to take any questions if anyone has any.
Very nice talk. So it seems like this like generative model that learns this like nuisance parameter is somehow inherently good at being, or good at generalizing into different domains. Seems like that's what you're implying.
Yeah.
Are there cases where that doesn't really hold?
Yeah, that's a good question. So there are all sorts of generative networks. There are some that are designed to kind of deterministically map one image to like another image. The good thing about the one that we're using here is it's designed to do this in a multimodal way. So I take an image and I map it to a distribution over images, so I can see all sorts of different things. Now that being said, if you're not able to successfully learn this kind of multimodal map, then your chances of improving robustness are kind of low. So all this kind of critically depends on how well you can learn the generative model. And another good direction is just figuring out how we can more effectively do this, because this became a bottleneck for a lot of this research. Yeah.
Yeah, so I have a related question with regard to the problem setting. So I feel like, why can't you just think of the concatenation of X and E together as your input, right? So to that extent, the environment is a part of your state.
Yeah.
Basically, your assumption is saying that, okay, I know my input vector and I know which dimensions could be perturbed at test time. So I feel like that assumption actually gives away to like the extent to which, or like the space of perturbation or distributional shift that you can expect. And to that extent, it feels like you're making what people typically consider, out of distribution problem to like something that's in distribution under assumption. So for example, in the rotation example, if it's negative 20 to 20 degree, right? That's the space of perturbation considered.
Right.
If that's like a additional dimension in that state space, at test time, I make that dimension 40 degree. Like, would your method be able to generalize 40 degree?
Yeah. Okay, so we did some experiments here too, not in the rotation case, but we did kind of a setting where I have access to some very small distribution shifts, say some very slight shift in weather conditions. like say kind of very sunny to like only a little bit sunny. And then we tested on like completely dark weather conditions. And we had some actually really nice results there that showed that it actually still helps to improve further out of distribution robustness. But yeah, no, it's a good point. I mean, especially for the case of rotations, it's a little bit synthetic because we know kind of how the state is going to be perturbed. We know that there's some components that are going to change, where there are other components in the data that are not going to change. The key point for a lot of these applications is that, like, for example, in medical imaging, we don't know which components of the data are going to change. So that actually needs to be learned through some sort of disentangled representation. But yeah, no, that's a really good point. I think that's actually a very cool direction for future research to see if, you know, if you do learn this distribution shift, can you go even further out of distribution and still perform well? Does that kind of answer what you were thinking?
Yeah, basically just out of distribution, not with respect to the original input, but with respect to the function.
I see.
Be able to be robust to that.
Yeah, because I mean, one thing to remember here too is that we're not getting any more data than anyone else is getting. Like all classifiers are getting the same amount of data. It's just that the way that you use it, I guess, is very critically important here. So it would be the case that if we were getting, like say, unlabeled data from the out of distribution set, and we use that to train the generative model, that maybe would constitute an unfair comparison, right? But the fact is that we're just reusing the data that we already have to do well. But yeah, I think this is a very cool direction for future work.
Another question.
Yeah.
So I'm not very familiar with this area, but I think I saw like a line fork which does similar things to domain computation. But so how does your method compare to those methods?
You know, I'm not really familiar with the work that goes on with domain confusion. I assume it would be quite comparable to what goes on here. But yeah, I'd have to look into that.
Yeah, just another comment. Yeah, since going back to Julia's point, it's quite your method is quite related to like what people do in robotics, like domain randomization.
Yes, it is quite related to. So that's actually really interesting because so domain randomization takes kind of a different approach a little bit here. I mean, a lot of elements are the same, but the optimization problem that's solved there is actually kind of different in that. Let me go back a couple slides here. So whereas we want to solve kind of a min-max problem like this, usually in domain randomization, you think about replacing this max by just some expectation over distribution. So that's also a really nice problem, which has like very strong relations to this problem. I mean, you could even think about kind of you could think about domain randomization as just being a particular, if this set P was just some distribution, like a singleton of some distribution over environments, then that would be exactly the same problem there. So for some choice of lambda, that's kind of the same idea as domain randomization. But the interplay between these two problems of kind of minimizing the expectation overall domains and minimizing over the worst case domain are kind of the two like fundamental approaches I would say toward like out of distribution generalization here. And whereas it may work practically just to do empirical risk minimization, I think the mindset of doing well even in the worst case is also like a pretty useful one here.
All right, are there any other questions? And by the way, the remote folks, you can just unmute yourself and speak if you want. Cool. I think if there are no other questions, we can end on this. Thanks a lot, Alex. And don't forget, there's food over there. Let me bring it up.
Thanks, guys.
Thank
Yeah, this is very interesting stuff. So I've been thinking about similar things in the context of reinforcement. Oh, really? Yeah. So basically, like your outer loop is like unifying, I guess, like maximum objective.